So hi everybody, welcome to this third video on single phase equilibria. So here we'll be going through a general phase diagram of a single component system. So we have already studied Gibbs phase rule, which states that F is equal to the number of degrees of freedom is equal to C minus P plus 2. Now since it's a single component system, C stands for components, right, and it is single, so I have to write that 1 minus P plus 2, which will boil down to 3 minus P, which means any degrees of freedom, F degrees of freedom is given by 3 minus P for a single component system. Now let us go through the salient features of this general phase diagram. Now the first thing to observe is when only one phase is present in a single component system. So for example, if this is your single component, so where all the single phases, if this is your single phase, so where all single phase is present. So for example, you can look at this is all single phase, right? Or you can look at this is all single phase, or it's a single phase, or it's a single phase, right? Or even here, for that matter, this is also a single phase, right? So wherever there is a single phase present, so let us go through that first. A, when only one phase is present in one component system, F is equal to C minus P plus 2. So this is given by, we have already seen that this reduces to 3, and therefore if only one phase is present, it is 3 minus 2 is equal to 2, right? So which means both, what are the freedoms that we degrees of freedom, what are the variables that we have here? One is your temperature and another is your pressure, okay? So which means both temperature and pressure can be varied independently at least over a small range. Without changing the number of phases. So which means so what does it mean? See here in this, if I take another color here, you can change pressure over a large range and yet you can still remain in that phase. You can change temperature over a large range and yet you can still remain in that phase. So by changing this temperature, you need not go to the next phase. That is what it means, which means over a certain range you can vary both pressure and temperature and yet remain in the same phase. That is what it means. So when both of them can be changed independently, the system is said to be bivariant. Bivariant meaning having 2 degrees of freedom. In other words, single phase is represented by an area on the phase diagram. By area on the phase diagram. Okay, now let us go into where two phases are in equilibrium. So if you look at here, whenever two phases, for example here phase alpha and phase beta are in equilibrium, here phase alpha and phase delta are in equilibrium, here phase beta and phase delta are in equilibrium, here phase epsilon and phase delta are in equilibrium. So whenever two phases are in equilibrium, in all this, what is the number of degrees of freedom here? When two phases are in equilibrium, so F is equal to C minus P. If two phases are in not C minus P, 3 minus P, and it is 3 minus 2. So when two phases are in equilibrium, degrees of freedom is equal to 1, which implies that pressure is not freely variable, if the temperature is set. So see here, or the same if you set the pressure, or if pressure is set temperature is not freely variable. Freely variable. So if you go through here, like for example, if you set pressure, okay, now if you want to remain on this line, you cannot independently change the temperature anyhow, which means you have to again change the pressure to stay on this curve to go to another temperature. So which means temperature is not freely variable. So you have to you set a temperature, here. There is only one characteristic pressure that can be if you have to stay on this curve. If you want to set a temperature here, there is one particular pressure here which you need to allocate to stay on the curve. You cannot independently keep on varying, just like how you did here. You can keep on changing, nothing, you would still remain in the same phase. But here, if you want to stay in equilibrium between these two phases, if you set a temperature, you will also have to set a certain pressure. That is what it means. No. Okay. Yeah, fine. Okay. In other words, Single phase is represented by area on the phase diagram, by a line on the equilibrium of two phases. And by line in the phase diagram. Okay, now let us see what happens when three phases are in equilibrium. So can you just give me those points wherever three phases are in equilibrium? Okay. See here, at this point three phases are in equilibrium. Which all? There is an alpha, there is a beta, and there is a delta phase. Three phases are in equilibrium. So is the case here, where here it is alpha phase, beta phase, and gamma phase. Which is there? So is the case here. There is no, not this one. Okay, we'll come to this. So there are basically 2 points. So where three phases are in equilibrium. So let us see what is there. When three phases are in equilibrium, your F is 3 minus P. If three phases are in equilibrium, 3 minus 3 is 0. So, and the system is said to be invariant. With degree of freedom 0, system is said to be invariant, meaning that it has no degrees of freedom. So which means this special case can be established only at a definite temperature and pressure that is characteristic of a substance and cannot be changed. So in the phase diagram, equilibrium of three phases is therefore represented by a point. And on a phase diagram. See those triple points, all the three, whenever there was a three phases in equilibrium, the point was represented by a triple point. Now four phases cannot be in equilibrium. So let us see what will happen if four phases are in equilibrium. So f is equal to 3 minus p. If 4 phases are in equilibrium, 3 minus 4 is equal to minus 1. But f cannot be negative, right? Therefore, 4 phases cannot be in equilibrium for a single component system. So, which means this point is invalid point. This is an invalid, so cannot exist. Invalid or forbidden. So that was your general phase diagram of a single component system. Thank you.